Welcome to Temple of Pwn, Part 14, and I think this will probably be the last Temple of Pwn. So, for the topic for today, I'm going to be talking about FSOP, which stands for File Stream Oriented Programming. Um, oh, yep, sorry about that. There we go. So, File Stream Oriented Programming, it's not necessarily new, but it's mostly the most notable reference that I've seen or noticed is from a presentation by Angel Boy at Hack in the Box in 2017. So roughly, I think libc 2.26, so right when Tcache was announced or implemented. So what this kind of means is each file structure has lots of pointers and flags and vtables and the such. And this is kind of just the modification or exploitation through those kind of pointers and stuff and flags to get what you want. So in the file structure, there's vtable for functions. So every time you fread, fclose, puts, printf, all that kind of stuff, it uses vtable within the standard out structure, which is this vtable right here. So it's going to point to a bunch of different functions, so it knows how to close it, how to or read from it, and that kind of stuff. Probably won't read from standard out, but it'll help print. But that's kind of just the general of kind of what a structure will look like. So here's actually kind of what it looks like. So the first 8 bytes will be the flags, as we can see here. Then we have these pointers, which kind of determine your current buffer location. So standard out's probably not. I mean, we'll be working with the standard out's buffer location, but it's not really important right now. But you might notice that they're all the same except for this last one, and that's mostly just to show that in this current instance, I believe. Let me check quick. Nope. Since all these are the same except for this last one, this is to show that this buffer is not or is buffered, so it won't actually print to the console or to the screen until a new line is sent or a carriage return or something of the sorts. So that's why there's a big discrepancy of 400 bytes right here. Whereas if in this example down here, it shows that this isn't buffered, so every character got printed, and this difference is only 1 byte. There's kind of a lot of intricacies between the read pointers, write pointers, and buffer ends and stuff. And we'll kind of talk about that a little bit, but not too much in depth. So by modifying certain pointers, in like this case will be these ones, we're able to get kind of a read write where, and we can get a data leak from it, and we can get arbitrary read and write. And then if you have the arbitrary read and write, you could possibly also modify the chain, which is this going to be file or pointer right here. And what this does, it points to the next structure of file descriptor. So I think standard out points to standard in. Yeah, because it's backwards. So standard error points to standard out points to standard in, and then standard in points to nothing. But with the kind of modification of the vtable or the chain, it's possible to get execution control, and it kind of also depends on the libc version. I'll talk about that at the last slide. So here's just a kind of example of the standard out between buffered and unbuffered. We can see that none of these pointers down at the bottom really matters. Just most of the difference is this one's going to store the data in the heap right away, whereas this one stores it right inside rate 3 or E3, I think right here. It's going to just store the one character inside itself, character by character when it reads. And there's pretty much nothing that you need to worry about right there with that. So just some of the protections that were recent or unprotections. With libc 2.24, they added a memory check for the vtable. So if you're able to overwrite this vtable pointer, it still has to land within a certain memory range within libc, otherwise an error will be thrown and it'll throw you out. And then in 2.26, they moved the vtable itself to a non-writable location. So I think this one was ran in libc 2.27, which this is a non-writable location. But as we can see in 2.29, they moved it back to a writable location. And this is, I think, 3.1, and this would actually be writable. So if we actually went to this pointer location, we could actually overwrite the pointers there to get further execution if we wanted. So some possible targets with a lot of this kind of stuff, you're actually going to have to go into the source code, and I'll show you a little bit about that. And there's lots of different kind of jump tables. So we're going to be modifying the standard out jump table to actually use this jump table instead, and it usually uses the IO file jumps instead of IO stream jumps. IO stream jumps I think is for, I'm not even going to guess, maybe stream compare and that kind of stuff, but that's probably not correct. I'm not really sure. But with that, I'll go into the binary that we're going to work with and go from there. So this binary is from Seccon 2020, so last October I think. It's a relatively new challenge, I guess. But at the time I didn't know about it. I actually found it while looking up this, a walkthrough for this, or like a challenge to work on for this kind of module. And I thought this was a pretty interesting challenge, which I was unprepared for in the, at least I guess. It was a lot more difficult, I guess I should say, than I thought it would be. But going through, we have an alarm. Looks like after 18 seconds that the alarm will throw, so crash after that. Baby heap calls menu. Read int, we look at it, just does read line, which is an f gets. And then an a to I, which f gets 15 characters, or 16 characters, might you remember that. It compares it to 1. If it's 1, it goes here. If it's not 1, it comes down here, which then it checks between 1 and 4. It's an invalid choice if it's outside that range, and if it is in that range, it says it's not implemented, so we only have the allocation available to us. So in the allocation, we have a read int, compares it to 0, so it has to be greater than 0. We have another read int, which this one says read size versus alloc size, so maybe there's a discrepancy there. We might be able to get something to overflow. From that, we can get a calloc of our var8, which is going to be our read int, so alloc size, so it callocs that. We'll save our pointer, make sure it worked correctly. Then right here we have this compare move. So it takes our allocation size, moves into EAX, compares it to our size that we gave, and then has a conditional move less than or equal. And then from that, it looks like it'll grab the lesser of the two, read that data into the buffer, so there's no overflow by that standard. And then it looks like it grabs the read size, adds it to the pointer, and then subtracts 1, adds them together, I guess, and then moves 0 into that buffer location. Which if we look right here, we then have a no byte overflow. I wouldn't want to say no byte overflow, no byte write anywhere, I guess, is how I'd phrase it. So this will allow us to write a no byte anywhere as long as it's pointed to by our read size. I'll phrase it that way. And another thing to notice in the main is that we have a counter of 3, which less than equals, so we have 4 total attempts to go into baby heap and then do all this. So within 4 calloc allocations, we need to be able to get execution on this binary. So keep that off to the side for now. So go into E2, not E2, go into exploit, whoops. I already have the little template going. So we have the create, the send, and then the interactive. I'll show you what it looks like when you just regularly increase this font a little bit. If we just run the challenge, we have just the 1, 2, 3 allocation size. We'll go 24, read data 80 SDF. Whoops, it needs a size. 24, 24, ASDF. Yeah, so nothing big or exciting there. Based on this LD, we probably know we're working with libc 2.27, and that's good to know because now we know that the vtable isn't writable, which if you didn't know we were working with the FSOP, I guess that doesn't really help you, but we know we're working with it, so it's something to think about. So just to start, we need to be able to have some kind of writability within libc. And the way this allocation mechanism, or not really mechanism, but the way calloc works is that if you allocate a chunk, it'll first go into the heap, as we know usually. So just run it here. Run allocation 24, 24 ASDF. So if we look at the heap, we should be able to see that it's going to be down here. Our data is in the heap. So if we continue, but if we allocate a chunk large enough, so let's say a million, garbage, we'll do all A's. do search pattern for our A's, just be the fastest way, I think. We can see that we're actually up in libc address space already, which if we check is going to be right after the actual LD is loaded and before the rest of the LD is loaded. And that's kind of just how the memory segments work. But if we allocate a chunk even larger than that, whoops, that was not, let's do even bigger. Oh my gosh, I pressed enter on accident. So let's say need to get an absolutely large size. I think that should work. Unless I broke it. That was interesting. Maybe it was just taking too long to allocate the space. But if you allocate it or make space even larger than one of those allocations that fit in there, the libc will actually go out and mmap you a new chunk right beneath the actual libc location. So we can use this because now we know that our data is going to be at a set offset if we allocate a large enough chunk to the actual libc. So we can use this to further get that arbitrary no byte right. So if we create a chunk of 0x2, so I have my notes, how much I actually need. Looks like 2 million hex. No, 200,000 hex. Okay, and then we need to figure out where we're going to write, but we'll do that later. And then A, just do a GDB attach. Not Python, Python 3. There we go. Invalid choice. Oh, size of 0 doesn't work. We'll go 10. And we can see that we have this chunk allocated and our data is right here. So with this ability that we have, we can write a null byte, one null byte at a time anywhere in libc. And what we're going to do is actually target the standard out pointer first. Oops, address. Because if we look back at the slides, percent quick, if we're able to modify the IO read end and IO write base of standard output, it'll modify or make standard output think that it's actually buffered and will print out all the data from the base to the current end. So if we put a null byte at IO base or end right here and make this a 0, it'll actually print out from 0, which I think is the middle standard error. So it print out from here onwards all the way down to where it actually thinks it is down here. So it print out all these almost 100 hex of bytes. And within there, we have at least a couple leaks, which we can use. And that's exactly what we want. Now the reason we need to also modify the read end is because of just some of the internals within puts. I'm not going to show you this source code at the moment because it's not too important to. I mean, it's important to know that this is just how it works, but I'm not going to walk you through step by step on it needs to be offset from a different offset to be recognized as buffered. You just need to know that these two both need to be nulled out. And it needs to be in the correct order, because if we null out this last byte first, it'll think it's buffered, but it'll fix itself before it actually prints it. So then it just goes back to E3. But if this one's 0, it'll stay fine, and then this one goes 0, then it'll print out and then fix itself, and we're good to go. Oh, I should have found the offset first. So we need to go to IO_2 standard out. Take this address from our current address, which is at 10, and do 5ED770 plus 1 because it does the -1 inside the actual binary. So go like that. I think. Oh, wait. We want to do the. I think that's the right one. Let me check though. We'll break a italic, continue. That should actually be there. Oh, we did the wrong first. We did the second one first. We want to do the first one first. Yeah. So yeah, do that as 6. So now we need to modify the second one, which if we just do that, I think it will yell at us and crash. No, it shouldn't crash. But if we allocate another chunk large enough, it won't fit inside the current mmap chunks, so it'll try and create another, or mmap another chunk. Let's go to 10 or 11. Come on, there you go. So it'll just push it further down. So we'll just need to grab the current address here and the current address at standard out. And this time we want to overwrite this guy. Should be this one. Set 10. So we have 7EE70. EE71, which for people who are astute at noticing patterns or something, that's actually just going to be 5ED761 plus 0x or 200,000 plus 0x1000 buffer that mmap automatically throws in there, plus the 10 offset from the end to the base. And then with that, if we run it again, it's taking so long because I have a wait 1 second so it buffers all the data correctly. We can see that the next time puts was called, it actually printed off all the data. And if we check out standard output to standard out, need the address, not the parenthesis. Not parenthesis. It fixed itself like we said it would. So now that standard out's fixed again, we don't really need to worry about it crashing accidentally, and we can also go through this data and now grab our leak. So looking through this, we have the first, it was the one from standard out, which I don't think is in this side. No, it's not. But I think it was at, it's going to print out a space and then 8 null bytes, and then it'll have a pointer. So we'll just take that. So we can do t is equal to p dot read until. We're going to just read this whole buffer, so we'll read until the space / space. Then we can do leak is equal to u64 of t from 9 to 17. That should give us our leak. We can do print the hex of leak just to see what we have. And we can check to see how this offset actually fits. And we can see our offset is at 3ED 8DB0. If we actually check out what's at this location, I believe this is, yeah, this will be should be in this, but it's not. Oh, maybe it's not. Maybe it's outside. But this is a pointer to the what is it called? To the it's to the thread safety check within the structures. So they'll make sure that they're the only one. So make sure they're atomic by setting a lock, which is going to be at this location. So this, if we were to overwrite this at some point, we just need to make sure it's an active pointer, and it doesn't really matter. But we can take this address and save it for later. So at this point, we'll just load our libc, elf libc.6.so.6. Do libc.address is equal to leak minus our offset. Now we should have everything working from there. So just for some future pointers, we'll grab the standard out address, libc.symbols of _io _2 _1 _standard out. And then we'll also grab standard in as well. just to make sure we know where they're at. So now we have our leak, but we still need to find a way to overwrite stuff. So if we do the same kind of method we had previously, but this time on standard in, we can actually modify where our data gets read into with fgets, which is what the binary itself was running within the read int or read line. And this is interesting because fgets doesn't actually work correctly under certain circumstances if you modify. We are going to modify fgets is, I need to check real quick because I don't remember off the top of my head. And I don't have it written down either, but I think it's going to be the right pointer. Might be the right base. But if we modify one of them, we can point to the beginning of standard input, because that's just how, run this quick. Because standard out input happens to be just right on the perfect boundary line. Put a underscore there. And by doing this, we can actually read more than 15 characters at a time through fgets, because it'll... Did I... Oh, I missed that one too. By using this buffer, we're able to overwrite all of it, and then we can just continuously get overwrites, or we can get another overwrite somewhere else. So IO underscore 2 underscore 1 underscore standard in. So I think it's this one. I'll have to check once we actually get there. But by modifying this to 0, we point to the beginning of the actual structure itself, which allows us to overwrite all of the bytes all the way down to the where it actually points down here at 8.4. So with that, we can modify all these pointers. And then once we get to the point where we can actually modify the base again, we could point this to somewhere else to get another write, because we can just continue the writing going as long as fgets doesn't get a new line or something. So to get the null byte in there, we are going to allocate another chunk. I'm just going to copy it, and then we'll check to see what the actual address was. So do that. I think should be fine. Still. Fake. Oh, I put a fake in there. That's for future. Go check out standard in. Alright, so I was mistaken a little bit. So by modifying, here we can figure out which one it was. Because I have the address, print that plus 10 plus 0x9EEA28 will give us 38, so it's going to be the second to last pointer, which is going to be the buffer base. Yeah, so modifying the buffer base, the next time fgets was called, it repositioned itself. Either when fgets was called or some other kind of standard input. So maybe it's probably when fgets is called now, because we're about to write data to it again. It modified all the other pointers so they all lined up. It just does it automatically. We don't have to worry about it. So now we can just write in 84 characters. So if we just send in a bunch of data, I think this will actually crash. Let's do a finish. And finish, and it crashed before I could check it. Darn it. One too many. So we can finish, put in all those A's. We'll finish again, go X. Standard in, we can see that we started writing here. And so now this is going to just keep going until we hit the 84th character, and fgets has already stored that we're offset by 84 characters already. So no matter what, even if we overwrite these two pointers, it'll still read in 84 characters into this buffer. And then at that point, if no new line has been found, it'll then read the buffer or pointers again to find out how much data we should be reading, or if we should continue, or if we should stop. So if we're able to overwrite these pointers, so if we overwrite these pointers while we're going, fill it up with 84 characters, the next X so many characters will be wherever we want. And with that, we're going to target the standard output structure. So we can do so right now the next send will be overriding that structure itself. So we're going to send in the flags because we don't want the flags to be necessarily broken for standard input. It could cause problems or it could be fine. I'm going to write this address doesn't matter because this is the read pointer inside, because we're overriding the standard in's read pointer, which won't matter. All that matters is that it's an actual valid pointer because it'll check. P64, we can just put a bunch of zeros because they'll all fix themselves. And then P64 of standard output plus P64 of standard output plus 0x2000. So at this point, we're going to be making it start at standard output and have the chance to write 2000 characters. You could honestly write this to anywhere. If you want to overwrite the free hook or the malloc hook, you could do that. You might be able to get something going with the free hook, possibly. I don't think we have any more mallocs available unless we can somehow get the calloc to function correctly, which could be another possible target, but we're just going to stick with overwriting the file structure themselves. So then we just need to fill up the rest of the data, and I'm just going to put no bytes in there. So this will fill up the rest of the 84 characters. So you see I'm sending a send instead of a send line, so this will make it still think that there's a buffer to read into, or that we should be writing to. So we just check at if we finish, it shows that it's not done reading. So if we actually check out the standard input structure, we can see that these pointers have all been modified to what we wanted, and see how the zeros didn't matter because it just fixed them right away anyways. We probably may have been able to put that one to 0 too, might have just fixed it for us, but not sure quite on that. So if we continue, let's actually do finish. We can show that we can have writability into the standard output. If I have it in, just go like this, and see that we're just now overriding the standard output. So there's two possibilities I'll show for exploitation within this, or with modifying kind of these. The first will be by changing the actual vtable location, because usually if we had the ability to write within the vtable itself, we'd probably just overwrite that with a one gadget or a chain or something to give us execution control. But remember, we had this vtable has to be within a certain range, and if we look at it, we're right now at the file jumps, and what we want is going to be this one, I think, the string jumps. And what's important about this is that most of these pointers are going to be semi-similar. So if we go to the second pointer with, or that's the second actual address within IO file jumps, we have IO file overflow. If we go to the second one within the string jumps, we have string overflow, which are similar enough. The other one that matters is, if we go to this, I think it's E8 plus 0x E8. This one, that might have not been right. Not E8. I'll figure it out in a little bit once we look at puts. But one of these pointers, I think one of these, I'm not sure which one at the moment, actually points to a same. Can we just look? Yeah, right here. These two right here point to the same function, and that function is actually called within puts, and what that function will call is then the second function, which, if we noticed, are slightly different. And how we're going to exploit this is that within, this is where you have to start looking at the source code. If we actually go to IO_string overflow, and we're able to make it past all these if statements, we can actually see that the file pointer is dereferenced, the allocation buffer is, and then it's called with the new size, and the new size is created from the old blend, which is also from the file pointer itself. So if we control the file pointer, we're able to get to this point, we can actually call whatever function we want. So we're going to make s or _s dot allocate buffer look like system, and then new size equal to bin sh location, so we call system bin sh. And that's the premise behind this exploit. The problem with that method is that it takes a lot of precision in actually having the right kind of offsets and values in memory at the time. So we'll just create a fake pointer, P64. We'll set up our flags for the standard overwrite or standard out overwrite. I'll go fbad 1800. We don't care about the next 4 pointers because they're not important to us and they won't be checked by the time it gets to our function stuff overwritten. Then we're going to need the bin sh, or the new, this will then grab the new value. So we'll take our bin sh address, which we don't have yet, and if we look at the code, I'll increase the size a little bit. We can see that our new size is equal to the old blah, which will be our bin sh address plus 100 and then, or times 2 and then plus 100. So we have to make sure that our bin sh actually conforms to that stuff. So minus 100 divided by 2, fake plus equals, we can do more zeros, times 2, fake plus equals, just copy this one again. These two need to be the same because there's a check whether, where is it? I think it's, I can't find it at the moment, but there is a check to make sure that those two are either equal or one is greater. And if they're not, then it'll throw an error or continue down a different execution path. It might be before this function's even called. So we need that, P64. Need a P64 here. We can do 8 or 0 times 8, fake plus equals P64. This is the standard file lock, which will be called no matter what, or this location, so we're going to need just a valid pointer. I'm just going to do standard out minus 8, that should work, plus equals P64. We can do another 0 times 9. A lot of times you might need these pointers where I'm just putting 0 to actually be something that's more valid, but through testing I just found that most of these can be 0 instead of actually realistic looking flag values. And now we just need our jump table, which I don't have in yet. The address for that is going to be at an offset of libc dot, I would usually just do symbol and then look it up, but this libc doesn't have that symbol loaded, equals plus, what was it, 0x3e8360, and that's just through some trial and error also to find which one it was. And then now we can have our IO string jumps vtable, and then next I'm just going to add 2 more, P64 of, we'll go 0x1, and then fake plus equals the P64 of 0, or standard out. So I'll explain the standard out one and then the 0 or 1. Line 3. I am. Good catch. So the reason I added that standard out at the bottom is that because, whoops, bin sh is not defined. We'll define that. Let's put a 0 for now. Actually, we can just find it. We can do libc dot search for bin sh, and then we need to grab the next because it's an iterable. I think that should be right. Normally in this case I wouldn't do that. I'd make sure that the bin sh address actually works because we're doing the minus 100 and divide by 2, so you have to make sure it's actually a possible location for that, but I already know what works for that, so it's fine. We actually never sent that data though, did we? Nope. So if we do a p.send line now to end the buffer, fake, this could actually crash before GDB catches it. Yep. So we'll move GDB before to see what it actually looks like before it actually gets to the puts. And we'll step through puts a little bit. So if we check out, we just finish this, check out, oh no, standard out, there we go. We can see that we overwrote standard out. We might actually be off by 2, 3 right here. So that one should be, yeah, I think we're off a little bit. Let me check real quick. Fbad, oh, this should be 0 times 4. Let me make sure to 2, 8, 9. That should be good. Now if we go back to it and check again. Finish. Standard out. There we go. Now we have our pointer to the table right at the B table overwrite spot. And we see everything looks good there. We have a 1 here, and then this one is we wrote to standard out, so it's just point back here. And the reason we did that is because if we break at puts, this libc isn't showing it, but I'm pretty sure this address is actually io underscore list all. Okay, it's not that. Okay, I've got no idea what this actual address is, but normally this will point to standard error, standard output, standard input, I think. And this one, it's not error, is it? This is just a garbage. That's something. But anyways, the problem with this is that if we break at puts and continue and then step through it, don't care about that, right here we can see that it's actually grabbing standard output from a static location every time, and that's where our location is at, is where we wrote that standard output to. But if we continue through puts, we can see that we can get to a call. I don't think we care about that call. We definitely care about that call. Why do I not remember that call? Something is slightly off from what I remember doing. And why is it asking for input? Okay, so we'll break at that call and step into and see what it's actually doing, because I don't remember that call being there. Break at puts, continue, skip past this ABS. We can probably walk through some of the flags and check to see what they look like. Compare to 0, jump if equal, compare exchange, jump if equal. I think we might have messed something up within that. Let's see what this call is. It's syscall 0xCA, which, what is that? Syscall table. So just a little side tangent because I'm just kind of curious. CA Futex. Okay. Whatever that means. Anyways, that shouldn't... Oh, maybe it's because of this pointer. Maybe that... Because I actually used the correct address last time. Let's do... I can do libc.address plus 0x3e d8c0, and that's the location of it. The actual mutex lock for standard out, I think. Break at puts. So I think it might have just been waiting for the lock to... Oh, that could have been it. Maybe it was just waiting for the lock to finish. So if we check out the address of standard output, -8. Yeah, that's the problem. Is that I chose... It has to be a valid address that's equal to 0, because otherwise it thinks that it's in use at the moment, because it's a mutex lock. That's what it's called. Okay. Anyways, continuing on. Come through here. Then we get to this call within R13 plus 0x38, which if we look at R13, that points to our jump table. And if we go 38, 1, 2, 3, 8, that's not the address I thought it was, but that looks right. It brings us to IO default XS puts N, which if we step into it, we can walk through it a little bit. There's nothing really too interesting here. It's just that does RAX plus 0x18, which is going to be our jump table again, and that's why we needed the string overflow. So, if we remember back, we just need to pass all these modifications, and I think we've already done most of them because most of the checks are within the flags, and we don't have IO rights. I don't think we'll have this one, but if we do, it's not going to affect us. Otherwise, the position size has to be equal to the IO blend of FP, which this plus flush only, which I'm guessing this is the one that I was thinking of with those two need to be the same value. That check right there. So jump if equal, blah, blah, blah. Don't really have to go realize what's happening instruction by instruction. What just matters is that we come down to this RBX plus E0, which RBX points to our location of standard output. And we do plus 0x E0, which will be our location where we put the 1. So with that, if we step in here, we should see that we have bin sh and RDI with RIP being 1. So I just need to have RIP be system. So we can do libc.symbols of system, and we should be able to get a shell. And look at that, we have one. So that's one possibility of exploiting the binary with modifying the actual vtables here. I'm going to show another one of using actual fake structure itself, because there's no checks to make sure that the standard in or standard error actually look like they're in the right spot. So I'm just going to comment this out quick. And we'll create a fake one within the heap so we control it entirely. I'm just going to copy and paste all the data, and I'll walk through pretty much. It's pretty much just going to be the exact same as the last one. Put it right here. So we have the flags. 6 is, again, is 0. This time we just have bin sh entirely. We have 0. The lock, because the lock is always needed, 0. And then we're going to do IO string jumps minus 0x28. And then system. Times 2. We only really need one system, but it's just at that offset that I wanted to, or I just thought it'd be easier that way. And then here we're going to do plus 0x8. That's good. So then if you remember, E0 pointed to the spot where we put system. So E8 is actually going to point to where standard out's at. So if we overwrite that with our location of our fake one, fake is equal to p64 of libc.address minus 0x. Oof, what would that address be? Do I have it saved? Oh, by golly, I do. 3000 plus 0x10. So now when we overwrite, this chunk is going to overwrite the standard output pointer that is grabbed with inputs and make it look like our fake chunk that's on the heap at this location, if I actually put it there, is actually standard output. So if we go back in and break at puts, libc.address plus 0x3ed8c0. String jumps, of course I didn't name it that. Oh, I just called it jump. Okay, system's not defined. Of course it's not. Okay, anything else I missed? I think that should be everything. If we break at puts again, continue, step through until it grabs it from RBP, or puts it in RBP, and check to see that this is actually going to be our heap value. So what I did here is that I modified, if we look back, you can see that I did the jump table, or the string jumps, so we're still using the string jump table, but minus 0x28. What this does is it lines up the first call right here, R13 plus 0x38, to be the actual function. Let me check, because I don't remember off the top of my head. Plus 0x38, this one, which is going to be not printable. I know it's within this file. It's like the last one. Let me find it quick. Idle string finish, which similarly has another pointer dereference to a function call, but this one has like a lot less you actually have to walk through before it actually happens. All that you have to do is make sure that the buffer base and with the flags is, and with that, oops, didn't mean to click on it, doesn't happen, which we can do by just making the buffer base 0. Well, we can't make buffer base 0 because we need that here. But we can make that 0 by making this 0. And then we own the free buffer more easily because it doesn't affect the after pointer of standard output and standard input like the last one could have. So the reason we didn't use just overwrite standard output and do this is because this ×2 would have overwritten the standard output pointer itself, and it just causes problems. So by faking it, we can step into this call. It'll check to see RDI, which is not going to matter. And then we can just see that it goes straight into the call of system. And we get a shell that way too. So that's kind of all I had for the exploitation of FSOP. A lot of, I guess both these examples are kind of useless nowadays, because if you look at 2.33, even 2.3 or 2.9, these function calls themselves are gone. It just frees them now instead of calling a function to free them. So you're actually out of luck with that, having the ability to do this method, but like I said earlier, that function, or the v table itself, is writable now, so you might just be able to overwrite any of these string pointers themselves, or the function pointer to these strings functions, and then have execution through that also. Another method we could have tried is the ability to modify the file chain. What that would have done is, if we modify, let's say, standard errors chain to point to the heap, and we have a fake structure there, we could make that be invoked, the function table, or the v table, be invoked when it tries to free everything when exit is called, which, based on this binary, exit will be called a lot if you fail at something. Yeah. Actually, this one, yeah, that would work. Either when exit's called, or if you went through the main and it returns back to libc main, it'll call exit for you. And in that time, the file structures will be closed, and you could get execution through that too. But yeah, thanks for watching. Are there any questions? No?
Very cool. Thank you for presenting.
Thank you.